What we're going to do in this video is we're going to talk about how we add to the body of knowledge in a discipline, such as kinesiology or physiology or one of the other science disciplines, chemistry, biology, whatever it happens to be. Before we start, however, I'd just like to say that periodically, while you're watching this video, you need to pause it so that you can take notes, so that you can think about what's being talked about, so that you can try to answer questions that I might pose as we go through the video. Okay, well, what is the process by which people acquire knowledge about kinesiology, physiology, or anything for that matter? The process is science. What I'd like you to do now is to take a minute to think about and define the term science. So go ahead and pause the video here. Science comes from the Latin scientia, which is to know or to discern. One definition of science that grows from this is it's the systematic study of the universe, and by this we mean the natural world, and its many parts, and that includes humans and how we function as humans, in other words, physiology. A second definition of physiology is that it's that branch of knowledge that produces theoretical explanations of natural phenomena based on observations, studies, and experimentation. Scientific knowledge allows us to describe and predict the natural world, and you can see from the definitions that we've just presented, science can be considered two things. First, it's the process we use to gain knowledge about the natural world. Second, it's the knowledge, and it has to be organized and reliable, information about the natural world. What are some important reasons for us to study science? And so again, you might pause the video and give this a little bit of thought, see what you can come up with. If you're very pragmatic, you might have said, so I can graduate, get a job, and live my life. However, science does allow us to answer lots of different questions. It might help us to figure out how we can feed a world population that soon is going to be over 10 billion people. It might also help us to predict the conditions that can lead to a tsunami and to be able to target those areas of the world that are most likely to be hit by a tsunami. More specifically, we might say, what are some important reasons for us to study physiology? And again, pause the video and think about this a little bit. What is physiology? Why do we need to know it? One of the answers I would give is that every one of us has a body. We can't avoid that. Everybody has a body. None of us are just mind. And so knowing physiology can help us to know how we take care of ourselves. What do we do that keeps ourselves healthy and fit? But more specifically, we might be able to think about something like, what is the role of exercise in preventing chronic disease? That's something that we can learn about through science. We might also think about how, for a disease like Parkinson's disease, where certain cells die off, how can we coax other cells into becoming those cells that have died off? And so again, most of you know about stem cells and that they do have the potential to become other cells. Well, how do we learn about physiology? How do we know what we know about functioning of the human body? Like all other sciences, physiology has been developed through the process of discovery and analysis using what's known as the scientific method. All of you have studied the scientific method at some point. For some of you, it may have been as long ago as middle school. Others may have studied it in high school, and some of you may have even talked about the scientific method here at DePauw, and I'm sure those of you who've taken Intro to Kinesiology have done that. The scientific method is the process by which scientists collectively and over time attempt to construct an accurate, that is, reliable, consistent, and non-arbitrary representation of the natural world. And again, as we've mentioned several times, functioning of the human body is a part of the natural world. Before we continue on with a discussion of the scientific method, I just want to quickly review a few other ways of knowing beyond the scientific method. The scientific method is relatively new in human history, but we've known things for thousands of years. One of the ways that we know something is we know it because it's always been true. And this is what's known as tenacity. Coaches demonstrate tenacity quite a bit. They tend to coach the way that their coach coached them. And they know that this is the correct way to coach because that's the way that they've always done it. Another way of knowing is because you learned it from an authority. And so an authority might be a professor that you have. Could be a textbook that you've read. Today's day and age, it might even be something that you've read off of the internet. A good illustration of how authority is a way of knowing is to look at the Ptolemaic view of the solar system and Galileo. And Ptolemy, as most of you know, said that the Earth was the center of the universe and the other planets and the sun orbit around the Earth. Well, Galileo took his telescope and he studied movements of the sun and the planets and stars, and he said, well, this doesn't appear to be right. I think that we have a heliocentric solar system. Well, the church didn't like that, so they threw Galileo in jail, and they said, well, we're going to kill you unless you say that Ptolemy is correct. And so Galileo decided he'd rather be alive than be right, and he did say, no, I'm wrong. Ptolemy's right. The Earth is the center of the universe. Another good example of authority would be Galen. Galen was a physician to some of the Roman emperors. He also was a physician for the gladiators, and he wrote thousands of pages about human anatomy, and for over 2,000 years, he was indeed the authority when it came to human anatomy. During the Middle Ages, questioning Galen's anatomy was questioning authority. And it was believed at that time that authority came from God. So to question authority was heresy, and it was punishable by death. And so it took somebody who was very, very courageous to actually question authority and to stand up to that. Here in this woodcut, this is a woodcut of an anatomy class, you see the professor sitting up here at the podium, and here he has his text of Galen's work, and he reads from the text. Down here are the students who are gathered around watching the barber. This is the barber who does the dissection on the cadaver. One of the reasons that the authority, the professor, sat up here was because there were no preservatives to use with the body, and so the body deteriorated really quickly and it smelled really bad. So the professor got as far away from the rotting cadaver as possible. Another way of knowing is what's known as intuition or a priori. Something appears to be self-evident or it agrees with reason, and so it must be true. And so if you go to western Utah, southwest of Salt Lake City, and you look out to the northwest, it's clear that the Earth is flat. And certainly several thousand years ago, people did believe the Earth was flat because it clearly agreed with reason, and you could see that it was indeed flat. As people thought about the way that we think about things and learn, they developed what was known as deductive reasoning. In deductive reasoning, we go from general statements, these are known as the premise, and we go from there to specific conclusions. The classic example of deductive reasoning goes back to, again, Greek times. And we make a premise, we make a general statement, all men are mortal. Socrates is a man, therefore Socrates is mortal. And the conclusion, Socrates is mortal, comes from the premise. Another example might be all mammals have kidneys. Humans are mammals, therefore all humans have kidneys. The accuracy of our conclusion clearly depends on the accuracy of our premise. And so here we have an example. All NBA players are tall. Earl Boykins, here to the left in the picture, is an NBA player, therefore Earl Boykins is tall. Well, you can see that our premise is not quite correct. This guy was about 5'5", 5'6", and so he wasn't even tall for the general population, let alone for NBA players. Now, the scientific method consists of a number of steps, and the first step in the scientific method is to observe and generalize. Some readings say that the first step is to create a hypothesis, but hypotheses always grow from observations, and so the first step is really to observe and generalize. And here we use the opposite of deductive reasoning. We use inductive reasoning. So now what we're going to do is we're going to go from specific observations to general statements. An example of that would be all observed cats have fur. This is a specific statement. Therefore, all cats have fur. That's our generalization. Another example might be every frat guy I see drinks beer. Therefore, all frat guys drink beer. Again, our conclusion really is dependent upon our specific observations. And I obviously haven't observed all frat guys in all situations, and so I can't know that all frat guys drink beer. Another example might be every crow I've seen is black, therefore all crows are black. And so again, you can see that our general statement isn't correct, and that means that our conclusion is not going to be correct. However, inductive reasoning is still important to the scientific method and to science. It's important because we can actually use inductive reasoning to make a prediction, or what would be referred to as a hypothesis. And this prediction can then be tested. An example of a prediction that we might make relative to physiology is, I predict that lifting weights will make elderly men stronger. Is this something that can be tested scientifically? Well, certainly it is. And so we can go out and recruit elderly men, and we can divide them up and put half of them in a control group and put half in an experimental group, and then have them weight lift and see if, in fact, they do get stronger as we progress. What I'd like you to do is to think about inductive reasoning and see if you can come up with a few examples of how you might create predictions that can be tested. So again, pause the video and see what you can come up with. We're going to use blood pressure and fish oil to illustrate this. And so an observation is that rats given fish oil supplements have lower blood pressure than rats not fed fish oil. Another observation is Canadian researchers have shown that fish oil supplements lower blood pressure in cats and dogs. And so now we'll generalize, and we'll say fish oil lowers blood pressure in all mammals, including humans. This is also a prediction. Is it a testable prediction? Can we design an experiment to test this prediction? And you know that certainly we can. So again, we can go out and we can recruit subjects. And we can divide them up. If we want to have a good study design, we're going to have a control group that doesn't get fish oil. And if we're doing this the best we can, that group is actually going to get a placebo. And the two groups, the experimental group getting the fish oil and the control group getting the placebo, won't know which group they're in. And again, to make the design as strong as possible, the technician who measures the blood pressure also won't know what group a particular subject is in when she's measuring the blood pressure of the subject. This is what's known as a double-blind design, and that's talked about in the reading on scientific method and development of vaccines. And to make it even stronger, what we're going to do is what's referred to as crossover design. And so after several months, what we'll do is we'll switch the two groups. The experimental group who was taking the fish oil will be given the placebo. And the control group who was taking the placebo will be given the fish oil, and we'll see if the results reverse themselves and flip-flop. And so again, that's called a crossover design. Again, as we've seen, we start with observations and we generate predictions or hypotheses that we can test. And so the hypothesis is a tentative statement that explains the observations. It's important that it has to be testable. What makes a hypothesis scientific? Well, what makes a hypothesis scientific is that it's testable. And so there are times when people create hypotheses that really aren't testable. Well, what I'd like you to do is see if you can't come up with an example of a testable hypothesis. Sticking with our fish oil and blood pressure example, we'll come up with a prediction that we can test. A 10 milligram per day fish oil supplement taken for 1 month will lower blood pressure in people with high blood pressure. And so again, you can see that clearly this indeed is testable. And as we've said, we can get a group of people and divide them up and have half be in the experimental group and half be in the control group. Another hypothesis we might make is passing through a black hole increases human longevity. Is this hypothesis testable? Not really. And that means it's also not scientific. We can't test it. Once we've developed our prediction or our hypothesis, then we have to design our experiment or our study. And we need to do careful planning, and we need to design a study where we control for all variables with the exception of one or two. And so using our fish oil and blood pressure examples, see if you can't think of some variables that have to be controlled for. Well, if you said sex, age, activity, diet, all of those need to be controlled for because they all have an impact on blood pressure. We know that women tend to have lower blood pressure than men. We know that blood pressure increases as we age. And so that would be an example of some things that we do have to control for. Once we have a well-designed study, now what we have to do is go ahead and collect and analyze our data. And I need to emphasize that it's really important that you have very careful and very precise measurement. Oftentimes in labs, we tend to want to hurry through so that we can get done, and our measurement isn't as careful and precise as it needs to be. If you get bad data, then your research is going to be bad. You need to re-ask yourself if your data are biased. If you did a good job of designing your study, there's a good chance that your data won't be biased. If, however, you decide that the data are biased, then you need to redesign your experiment. If your data aren't biased, then even here what we have to do is refine our hypothesis based on the results of our study, and then we need to repeat our experiments. If the results aren't repeatable, then you have to look at your hypothesis and see if you can't figure out what might be wrong with it and propose an alternative hypothesis. And I just want to state here that it's extremely unlikely that one study or experiment will ever prove anything. Proof only comes after many repetitions of a given experiment. And that's because we have to look at different groups of subjects. If we used male subjects, we need to test and see if this is true in female subjects. If we used college-age people, we need to test older people and see if the results hold there. And then we draw conclusions. And what I'd like you to do is think about what we mean by a conclusion from a scientific standpoint. This is different than the conclusion that you would make for a paper that you're writing in the humanities. And so if you're writing a paper for a history or philosophy class, you finish with this concluding paragraph. But that's not quite what we mean here. A scientific conclusion is slightly different than that. Here we generalize our results from our specific group that we've studied to the larger population. And so a conclusion is the necessary consequence of two or more propositions taken as premises. Or it's also the logically necessary end reached by reasoning. This is just simply a flowchart showing you the steps in the scientific method. After we've repeated the experiment enough and we've revised our hypotheses, we may be ready to state something as a theory. In the next video, we'll talk more about what we mean by theory, hypothesis, and even fact. Let's look at a study that was done in '97 to illustrate the idea of bias. And so this study was looking at cancer rates in Utah compared to Washington, D.C. And you can see that cancer rates were much higher in Washington, D.C. than in Utah. What do you conclude from this data? You might be tempted to conclude that urban living increases the risk of cancer, but we have to go back and look at that study and see how well they controlled for possible sources of bias. And sources of bias here can include population profiles. Cancer rates differ by gender, race, and age. Is the population of Utah, is their gender, race, and age distribution the same there? Cancer is also related to occupations. Certain occupations expose people to carcinogens much more so than other occupations. We need to look at mobilities. It is possible that people in Utah who are diagnosed with cancer decide they're going to move out and be closer to the better cancer centers, which might be located in urban areas like Los Angeles. Perhaps Chicago, Washington, D.C. And we also need to look at what kind of preventive health care there is in a particular area. And lastly, I just want to reemphasize the importance of repeatability to the scientific method. And so you've made your prediction and designed a hypothesis. You design a well-controlled study and you carry it out being very careful with your data collection. Your data support the hypothesis. Has it now been proven? Well, practically speaking, again, one study rarely ever proves anything. We can indeed disprove a negative with one study. There are no crows that aren't black. We only need one study to disprove that. Other studies require multiple repetitions, usually by multiple laboratories. And so if you're watching the news and they say a new study proves something, you know that more than likely that is not the case. In the next video, we again will talk a little bit more about things like hypothesis, theory, fact, and those kinds of things.